Polyprotic acids are acids with more than one ionizable proton. They have different Ka values. Remember our acid dissociation constant values? Okay, for each time a proton is donated. For example, Ka1 is going to be greater than Ka2 and greater than Ka3. We only really care about Ka1 because we only use this one since Ka2 and Ka3 are technically insignificant because they are extremely weak. They have very, very small values. So equilibrium is mainly established by this Ka1. Let's have a look down here, okay? So polyprotic acids, there are two common types, diprotic acids and triprotic acids. Diprotic acids have 2 protons to ionize. Triprotic acids have 3 protons to ionize. Regardless, all of these need to ionize in sequential steps. Okay, so let's have a look at this question over here to illustrate. We have our H2CO3, so this is going to be our acid. I'm going to add it with our water so that it can dissociate and create and ionize our anions and cations. Obviously this is an acid, it donates that proton towards this thing over here, so this has one less H. So now as we can see, there's only one H there. It got rid of one H. Okay, so it's a little bit less positive, hence why it's a -1 symbol here, and this received that proton from this one, so we have an H3O plus. Okay, we can create an ice table if you want, but we don't really have to. We can just look over here and pretty much know that when we create our ice table, this one and this one are going to be our 2 x's. Okay, see the 20-minute version if you want to see the ice table. Okay, the video link is in the description. So we have our 2 x's over here, and x times x gives us our x squared. This one here would be our only reactant on the bottom, and it would be 0.040. Okay, because that was our initial value of our H2CO3 as listed up over here, and then we have to be minusing x, right, because this is our negative change in our ice table. So then from here we can do our 0.04 divided by our Ka to see if it is greater than the 1000 rule, and obviously it's going to be greater than the 1000 if you were to calculate and divide this. So we can actually get rid of this 0.040 minus x and just keep it as 0.040. So now we have our x squared up here. You just do our multiply by 0.040 over here so that they can cancel out. If you do it on the right side, you got to do it on this side as well. You end up getting this. You just square root it. You get our x value as this. Okay, so this is our concentration of our H plus or hydronium, okay, which is going to be the same as our HCO3. So our pH is now going to be equal to negative log of that hydrogen, which is going to be this one over here. We place that answer. Okay, so this one is going to be our answer. We're going to be putting this into here. We get our pH as 3.89. What about CO3 2 minus? It would actually be the same concentration as our Ka2 because, like we said, we only use our Ka1, and because this Ka2 value is very, very weak, barely dissociates. Please try this question on your own. I'll be giving you the answer shortly. This is the answer.